Welcome everyone. Thank you for joining us today for this session of our HACC Tech Talk series. My name is Mario Ruiz and I'm today's host. In today's sessions, we have two 30-minute talks and the topic for today is HPC applications on FPGAs. We're going to start with optimizing communications for latency sensitive HPC applications on up to 48 FPGAs using HACC. So the presentation is going to be done by Marius Meyer, who is a PhD student at the Paderborn University and research associate at the Paderborn Center for Parallel Computing. His research interests include the implementation and optimization of HLS and OpenCL-based FPGA applications, multi-FPGA applications, and inter-FPGA communications.
Thank you for the introduction. Today, let me arrange it a bit here. So this talk that I will give today is to large portions actually based on a publication and talk I gave this year at Europa. And so most of you may already have heard of the Alveo Collective Communication Library, for short ACCL. This is a library that helps to scale out applications on multi-FPGA systems. And today in this talk, I will look further into how ACCL can be used to actually scale out applications in the domain of scientific computing. And therefore, we looked into a 2D shallow water simulation. So this brief overview. So here on the side, you can see some simulation output. So this 2D shallow water simulation can be used, for example, to simulate ocean tides or dam break scenarios. And the simulation that I used to extend with ACCL was already available and implemented in OpenCL. And the whole simulation loop was or is offloaded on the FPGA. So the whole data that's required for the simulation is actually located in the on-chip memory of the FPGA. And basically, this also means that if we want to scale, for example, to higher resolutions of the used surface or mesh, or if we want to just simulate larger areas, we may need to actually split the whole computation over multiple FPGAs. And there ACCL comes in. And actually, to scaling the simulation requires very low latency communication, because in every communication or in every simulation time step, we actually need to exchange data, and each simulation time step usually takes lesser than 25 microseconds. So in this time, all the communication has to happen. Yeah, so the multi-FPGA system that we used for this work is the Noctua 2 system, or the FPGA partition of the Noctua 2 system at PC Square, Paderborn Center for Parallel Computing. And it's recent PCI Express FPGA was equipped with these QSFP ports that offer high bandwidth and low latency communication. And this is also the case for the Noctua 2 system. So here we have in overall 16 nodes with 3 Alveo 280 boards each. Let me change my pointer. Yeah. And all these FPGAs are connected via their QSFP ports to an optical switch, which allows to directly connect the QSFP ports of arbitrary FPGAs to allow circuit switch communication. And additionally, we have an Ethernet switch connected to the optical switch, which allows to send data from the QSFP port directly to the Ethernet switch, and with that establish a packet switched network and to packet switch communication. So to actually utilize this kind of dedicated network is quite error prone and cumbersome, because usually one needs to implement all the network functionality from scratch for every HPC application. And there's actually where ACCL comes in. And ACCL offers additional level of abstraction and features that are quite common, for example, common communication tasks that are usually done in HPC applications. And this, of course, also comes with additional level of abstraction, also comes with additional resources that are consumed on the FPGA. And these resources that are missing can then, of course, be missing in the actual computations and calculations that are done by the application. So in the end, the question is, okay, how does ACCL actually affect the performance of HPC applications? On the one hand, by scaling out the application to multiple FPGAs, and on the other hand, by consuming also more resources on each individual FPGA. So the talk is structured as follows. So first of all, I want to talk about ACCL and give a short introduction about the structure of ACCL and how it works, and then give some brief insights into synthetic benchmarks that I did. And in the second part, I will talk in more detail about the actual 2D shallow water simulation that we accelerated, and of course give some insight into the performance evaluation over the whole Noctua 2 partition, which consists of 48 FPGAs. So this is I would say, user-side view of ACCL, so with very low detail. So ACCL implements a hardware architecture that allows to implement primitives and collectives directly on the FPGA. The core of ACCL is the Collective Communication Library offload, so the CCLO. And this basically executes the MPI-like communication on the FPGA and is connected to the either TCP or UDP network stack for the communication. And so the network stack then uses the queues of P ports and the dedicated network. The CCLO has to be scheduled, so the commands like send, receive, or broadcast collectives have to be scheduled at the CCLO via an ACCL stream and ACCL stream, and this is done either through a host control kernel, which is provided by the ACCL tool flow, and this host control kernel is then indirectly usually scheduled on the CPU by using the provided C++ API for ACCL. And this C++ API already implements calls like, as I said, send, receive, or also collectives like broadcast, reduce, and so on. And these calls will then be forwarded to the CCLO. Another way to actually use ACCL is to implement your custom control kernel that connects to the same interface. And with this custom control kernel, one can basically implement whole communication patterns directly on the FPGA. And the advantage of that is that we only have to call the compute kernel once and do all the communication instead of calling it for every communication task that we want to do. We will see later how this affects actually the performance. Overall, ACCL supports two different types of communication, streamed and buffered communication. And the following, I want to give you a short overview about what I mean by that. So let's say we have an FPGA board here and our global memory here, either HBM2 or DDR memory, for example. And then if we want to use buffered communication, we basically have two buffers in global memory that are relevant. One is the receive buffer that is used internally by ACCL and the CCLO, and then the destination buffer that will be used by our actual compute kernel, so the HPC application that will be running on the FPGA. So now if we want to send data, for example, from a remote FPGA to this FPGA here, we have to schedule a send call via the host control kernel to the CCLO. The CCLO will read the data somewhere from the global memory, pass it via the network to this FPGA here, and the data will be stored in the first step in the receive buffer on the global memory. In the second step, we will call the receive on the local FPGA. And by that, we will basically copy over the data from the receive buffer to the final destination in global memory. Then in the third step, we can actually use this data in our compute kernel, for example. So this altogether leads to the following quite simple communication latency model that consists of 2 times the latency to actually execute the host control kernel, or to basically to the latency that's required to pass a command to the CCLO. Then the latency to copy the message in global memory, and the general network latency. With stream communication, we don't use the global memory, but instead, ACCL also offers ACCC streams for transferring data. And in that case, we can directly send data from our compute kernel via an ACCC stream to the CCLO and send it over to a remote FPGA. And also the other way around, we receive data, it can directly be forwarded via an ACCC stream to the compute kernel. And by that, we can actually get rid of one invocation of a control kernel, because we basically just have one send and the receive happens implicitly by just receiving and forwarding. And we get rid of the copying, because the data is directly forwarded without this additional storage in global memory. So in the first step, we just synthesized ACCL in different configurations and looked into the resource utilization that we actually have just by using ACCL. And therefore, we have the following plot. So this is just a selection of the configurations that we tried out in our work. So we find all the other configurations in the paper. But I think these are three good examples that actually show what's going on. So first of all, we have these black rectangles, and these represent the resources that are utilized by the CCLO and all the ACCL kernels, for example, also the host control kernel, everything that basically implements the ACCL functionality. And all the remaining resources here are utilized by the network stack. For example, in this case, for the red one, this is the TCP network stack. And as we would expect, it consumes considerable amount of memory because it's quite a complex network protocol. Whereas for UDP, we have way lesser resource utilization, especially logic utilization, but also VRAM. Now, ACCL is quite configurable in a sense that it consists of plugins that offer certain functionality. This functionality can, for example, be arithmetic operations that may be used, for example, in reductions or compression and things like that. And if these plugins are not needed for the specific application, and in our case, we're always looking at the shallow water simulation, then they can just be removed from ACCL and we can further reduce our resource utilization. And in that case, we excluded the arithmetic plugin and the compression plugin because we just want to do point-to-point communication in the end. And with that, we were already able to more than half the logic utilization of ACCL in that case. So what does it now tell us regarding the performance? So before we started with the shallow water simulation, we looked into synthetic benchmarks and the overall message latency over different message sizes. So message size you can see here on the x-axis, so and the overall latency on the y-axis. And here, I just mentioned a few slides ago, we have the difference between calling send or receive directly from the host or from the FPGA. And this is something that we can nicely see in this plot. So first of all, we have this orange lines and the blue lines. These are the buffered and streamed communication when they are scheduled via the CPU API. And you can see that it already has a quite high latency from the start. And the reason for that is that we are using XRT, the XRT runtime on Noctua 2. And this XRT runtime comes with a quite high latency for scheduling kernels. And this is also then, of course, reflected in our communication latency. However, if we use our scheduling directly from the programmable logic, this is the PL buffered and PL stream here, and these are the lines here below. You can see that the latency, especially for small message sizes, can be extremely reduced. And this is because we can now just combine different communication patterns together and just execute kernel once, which does all the communication. And with that, we can basically hide this overhead of XRT in that sense. What you can also see here in the plot is the difference between streamed and buffered communication. So I already briefly mentioned the performance model that we built up, and the performance model is here represented by these dashed lines for all the different configurations. And you can see that especially for the buffered communication, the latency is, even for large message sizes, higher than for stream communication. And this is basically because of this additional copy operation that we need in case of the buffered communication. So with that, we want to go from the synthetic benchmarks and ACCL to the actual 2D shallow water simulation. And I already mentioned that this 2D shallow water simulation that we used already existed and is an OpenCL implementation that also already supported multi-FPGA execution on directly connected FPGAs, so a circuit switch network. And so you can see an example input mesh of this simulation here. So the triangles basically, so this is basically the mesh, the unstructured mesh that is used as input for the simulation. And yeah, this is basically the data that is stored completely in the local memory of the FPGA. So if we now want to have a larger mesh that we want to simulate, we have to partition it, and that could look like this. So here we have a similar mesh divided into 18 partitions, so indicated by the different colors. And each FPGA, indicated by these blue dots, is then responsible for one of these partitions. And you can also see that by these red lines between the FPGAs, that the FPGAs have to exchange now the data of the bordering partitions in every simulation step. And in the existing implementation, all these connections actually had to be physical connections via QSFP ports. So if we had 4 QSFP ports available, we could have at most 4 neighbors in this mesh. With our ACCL implementation, we are now using packet switch communication, so the limit is increased, and we can actually scale to larger numbers of neighbors. For example, in this case, we have already 6 neighbors for this FPGA here. And with that, we can also scale to larger, to larger numbers of partitions and to actually higher numbers of FPGAs overall. So regarding the communication, so I already mentioned that there is buffered and streamed communication that we can do with ACCL. And for the data exchange in the shallow water simulation, we actually use a combined approach. So here you can see in form of 4 different kernels, the simulation loop of the shallow water simulation. And we have this communication kernel, and every element of the mesh that needs to be sent to a remote FPGA, because it's a bordering element, is forwarded to this communication kernel. And this again will forward the element to ACCL to send it to a remote FPGA. So this is done in a stream fashion. So we will directly, via an ACCL stream, forward the data to ACCL. And ACCL will send it over to the remote FPGA, and on the remote side it will be stored in global memory. So this is the buffered approach. All the communication is scheduled by a custom communication kernel for the whole simulation. So we just start this kernel once in that case. And now if the data arrived from all the neighbors, it will be read from the global memory, also via an ACCL receive call, passed again to the communication kernel, and from the communication kernel back to the compute pipeline. And in that case, we are using the buffered communication because we cannot ensure in which order the data will actually arrive from our different neighbors that we may have. And to ensure the right order for our compute pipeline, we basically use this receive from global memory to just get the right order here. So based on the latency models that we actually came up with during our benchmark phase, we also extended the throughput model of this shallow water simulation by also considering the communication latency. So here it is that the communication latency can be hidden by updating core elements of the partition. So the core elements are elements that are not on a border to any other partition. So we don't need any data from remote FPGAs to update them. And so we can basically do these calculations while we are sending data to and from other FPGAs. So with this setup, we did basically two experiments. First of all, the weak scaling experiment, where we used or partition sizes of 6,000 elements per FPGA. And the performance results you can see here. So on the x-axis, we have the number of FPGAs that we use. And on the y-axis, we have the overall performance of our simulation in teraflops. The axes that you can see here and there are the performance values of our related work, where our implementation based on. You can see that this performance quite nicely matches with our UDP ACCL version that we implemented. But with the advantage that our ACCL UDP version is actually able to scale to much more FPGAs. So the highest number of FPGAs that the circuit switch communication was able to simulate was 10 FPGAs, and here we go up to 48 FPGAs. What we can also see is that we see a performance difference between the ACCL version that's using the TCP stack and the ACCL version that uses the UDP stack. And the reason for that is in the TCP stack, we are using a lot more resources for the implementing the network stack, which you can see here. And this also reduces the space that is available for actual application. And in that case, we were not able to synthesize design with the same buffer size than on the UDP stack, which means we had to reduce the buffer size where we want to fit our meshes in. So we could only compute on lesser elements per partition, basically, on each FPGA. And this leads then to the point that we cannot hide the communication latency as good because we have just not enough core elements to compute on. Also, we have here the kind of baseline model where the communication happens via PCI Express and NPI via the host network. And also here you can see that we, of course, have some performance improvements when scaling to more FPGAs, but we are heavily bound by the communication latency. In that case, the computation pipeline will just stall until the data arrives. And yeah, this is why we see this huge difference here. So with the strong scaling, this looks a little bit different. So I already mentioned our throughput model that we extended with our communication latency. And I mentioned our latency model for our buffered communication. And this now also has an effect in our strong scaling experiments. So in this case, we take a fixed number of elements for our meshes and then scale it over an increasing number of FPGAs. So you can see here again. And what we now have is that depending on the partitioning that we choose and also the size of the partition and the size of the mesh, we may have a different number of neighbors for our partitions. And for each neighbor that we have, we need to call basically a send and then a receive via the CCLO to send and receive the halo. So this basically adds this n max term to the communication latency equation, just because we have to do it for every neighbor. All the remaining part of the latency model stays basically the same. But what this now means for our performance is that, for example, for the 100,000 element mesh here, that if we scale to a higher number of FPGAs, we may still see a performance improvement. But in certain cases, if the number of maximum neighbors per partition increases, it may not only be that the performance is upper bound by a certain amount, but it may actually degrade. So it may be lower than before, just because we have more number of neighbors and more calls to the CCLO to send data. So this is a limitation that can be quite nicely observed here, and also in our performance model that we set up here. So with that, coming to a summary. So what have we done in this work? So first of all, we evaluated ACCL and the different communication approaches that are possible with this framework, and also spent some time to optimize ACCL and the network stacks for our Noctua 2 system. And we could see that ACCL offers high configurability depending on the use case. So we can, for example, exclude plugins to save some memory, to some resource on the FPGA, or choose the network stack depending on the communication pattern that we have. In our case, we looked at communication sensitive applications where network congestion doesn't happen that often. So that's why we also could use the UDP stack. That may not always be the case. Sometimes TCP may be required in that sense. And we also came up with these latency models for the different kinds of communication that we could then use in a second step to actually improve the performance model of our shallow water simulation, and also explain the strong scaling limitations that depend on the maximum number of neighbors in our partitioning scheme. Yeah, with that, I'm at the end of my presentation. Thank you.